All right, so next we have alternating series. So alternating series are basically just like any other series, except that they kind of flip-flop their signs. So it'll be plus, minus, or minus, plus. So that's what the definition is saying here. So B of n is just the non-flip-floppy part of it. And so if you wanted to start at a positive number, you would choose this guy. So this would be starting at positive. And then the only difference is that this one starts with a negative. But they're both alternating series. Notice that B of n is positive, or at least non-negative. So now that we know what an alternating series is, we can define the alternating series test. So this is another test for convergence or divergence. So if you have an alternating series, then if the B sub n, the sequence B sub n, if that's decreasing and the limit of the sequence B sub n goes to 0, then we know that it will converge. So let's apply that test to example 5.19. So this is B sub n here. So what we want to show is that B sub n plus 1 is less than or equal to B sub n. So that looks like 1 over n plus 1 squared is less than or equal to 1 over n squared. And certainly that's true because n plus 1 squared is greater than n squared. The next thing we need to show is that the limit as b sub n, the limit as n goes to infinity of b sub n equals 0. So we're just going to take the limit as n goes to infinity of 1 over n squared, and that is definitely 0. So we conclude that a given series converges. In the second example, b sub n is n over n plus 1. So the first thing we want to show is that b sub n plus 1 is less than or equal to b sub n. So this would be n plus 1 over n plus 2 is less than or equal to n over n plus 1. So in order to do this, I'm going to just cross multiply. So I get n plus 1 squared is less than or equal to n times n plus 2. So this is n squared plus 2n plus 1 is less than or equal to n squared plus 2n. This is not true, right? So this is saying that 1 is less than or equal to 0. So this is false. And we know that the alternating series test does not apply. And so at this time, we're not able to conclude anything about convergence or divergence with the alternating series test. However, notice that the limit as n goes to infinity of n over n plus 1 equals 1. So that's the second way that we're not allowed to use the alternating series test. So in general, the limit, right, so we have the nth term test for divergence. So if this guy goes to 1, n over n plus 1 goes to 1, but I'm still alternating -1, -1, this limit does not exist. So then by the nth term divergence test, right, that was in section 5.2, this does not converge. So also similar in section to what we saw in section 5.2 is that we can determine remainders for alternating series, but it's a lot easier. I think before we had the remainder was bounded above and below by the two integrals as it relates to the integral test. This one's a lot easier. It has a really nice form. So the remainder, same idea of the remainder as before, it's just less than or equal to the n plus 1th term. So for this guy here, Bn is 1 over n squared. So we know that R10 is less than or equal to the 11th term. So the 11th term being over 1 over 11 squared, 1 over 121. So we've bounded the remainder by 1 over 121. But let's say that we want to find n such that the remainder is less than 0.001, right? So now I'm saying I want to estimate the value of this alternating series, but I want to make sure that I'm not off by more than 1 over 1,000. So how far should I take my partial sum in order to do that? So we know that R sub n is less than or equal to B sub n plus 1. And we want this to be strictly less than 0.001. So this is 1 over n plus 1 squared. And so in order to solve this, I get that 1,000 is less than or equal to n squared plus 2n plus 1. And so I would just solve this polynomial inequality. You could solve that using, it's going to look like this. So you just want to know what intervals here are going to give that to you. So you just solve this. You could use a quadratic formula if you want, but that's how you work it. So it's just an algebra problem. Okay, so the last thing to cover is absolute and conditional convergence. So when you have an alternating series, you could consider the absolute value of that. So like, let's say you had negative 1 to the n plus 1 of 1 over n, for example. You could also consider just taking the absolute value of that. So when I take the absolute value of that, it's just 1 over n. This is a harmonic series. And we know that it diverges. But what about this guy? So one, I know that 1 over n plus 1 is less than or equal to 1 over n. And I also know that the limit as n goes to infinity of 1 over n equals 0. So when I don't take the absolute value of this, it converges. And this is actually called the alternating harmonic series. So this is an example of what we call conditional convergence. We have that the regular form converges, but when I take the absolute value of it, it doesn't converge, it diverges. So this is an example, again, of conditional convergence. If instead they both diverged, we would have what's called absolute convergence. And if we know that something converges if we know that if we take the absolute value, if it converges, then it would imply that the other guy converges as well, because it kind of serves as an upper bound for it. So we basically just did that example there. It's just an alternating harmonic series. So let's look at B. So I always want to consider the absolute value first, because if I show that the absolute value converges, I don't need to bother showing the other one converges. I will just use theorem 515 to be like, oh, they both converge, or converges absolutely. So we know that cosine will oscillate between -1 and 1. N squared is always positive. So this is really just cosine of n over n squared. And then the idea here is to compare it. And we're just going to do a direct comparison. So we know that the absolute value of cosine of n is less than or equal to 1. So we're just going to compare directly to 1 over n squared, right? The series 1 over n squared. So this is a known convergent P series. With P equals 2. So since the absolute value of cosine of n is less than or equal to 1, from here I can say the absolute value of cosine of n over n squared is less than or equal to 1 over n squared. Therefore, the bigger one being convergent implies that the smaller one is also convergent. And then the absolute value being convergent implies that the original is also convergent. You don't need to write that, you could just say absolutely convergent.